Hello there, virtual conference visitor. My name is Stijn Hendrikx. I'm a PhD at KU Leuven, and I'm going to present you my master thesis and my further work I did on this topic during my PhD. The goal of my work is to use multivariate regression as a model for applications such as pattern recognition, data analysis, and machine learning. We use a tensor decomposition to greatly reduce the amount of parameters of this model. Linear regression in one variable is regression in its simplest form. For example, it can be used to find a linear relationship between the price of a house and its floor area. However, if the relationship between these variables is not linear, you can use a more general model such as polynomial regression to better approximate it. Another possibility to improve the linear model is to generalize it to more variables. For example, we can add variables such as the construction year or the lot area. This type of model is multivariate linear regression. If we combine both generalizations, we end up at multivariate polynomial regression, which is even more expressive than the two previous forms of regression. However, using multivariate polynomial regression comes at a large cost, since the amount of coefficients of a multivariate polynomial is exponentially dependent on the degree and the amount of variables of the polynomial. This exponential dependency is commonly referred to as the curse of dimensionality, and this makes it infeasible to directly apply this model to large datasets. You can clearly see the curse in this plot. For example, a multivariate polynomial of degree 10 with 100 variables already has around 10 to the power of 15 parameters. Furthermore, the equation shows us that the amount of parameters depends on both the degree and the amount of variables with a factorial. To break this curse, we use tools from tensor algebra. Tensors are higher order generalizations of vectors and matrices. A matrix can be used to represent a grayscale image, since each pixel corresponds to one value. In a color image, each pixel consists of 3 values. This means that it can be represented by 3 matrices. We can stack these matrices behind each other, and we then obtain a 3D data structure which is in fact a third-order tensor. If we go one step further and add a 4th dimension to this tensor, we can use this to stack a sequence of color images on top of each other. This means that the video you're watching right now can be considered a 4th-order tensor. In general, a tensor is the natural way of representing data of dimensionality higher than 2. Another advantage of using tensors is the fact that it allows us to use tensor decompositions. Tensor decompositions are powerful tools from multilinear algebra, and they are the tensor equivalent of matrix decompositions, such as the singular value decomposition. In this work, we use the palyadic decomposition, since it has the ability to break the curse of dimensionality. The palyadic decomposition decomposes a tensor as a sum of rank 1 tensors. A rank 1 tensor of order 3 equals the outer product of 3 vectors. If this equation between the tensor and the decomposition holds exactly, and the amount of rank 1 tensors is minimal, then R is the rank of the tensor. While the amount of entries in the full tensor is exponentially dependent on the order n of the tensor, the amount of parameters of the palyadic decomposition is only linearly dependent on the order. This illustrates its ability to break the curse of dimensionality. So, our goal is to use multivariate polynomial regression as a model and make it feasible by approximating its coefficients with a low-rank tensor to greatly reduce the amount of model parameters. In our work, we use this model to approximate the Gibbs-free energy of a metal alloy. The crucial part of our approach is the use of the palyadic decomposition, since this allows us to develop an efficient optimization-based algorithm and an algebraic algorithm to compute the model parameters. To be able to apply a low-rank palyadic decomposition to the coefficients of a multivariate polynomial, we first have to rewrite this type of polynomial using a tensor. You can write a first-degree homogeneous multivariate polynomial using a vector that contains all its coefficients. If we generalize this to the second degree, we can see that we can represent this kind of polynomial using a symmetric matrix. If we rewrite this using the mode n tensor matrix product, which is a generalization of the matrix product, we obtain an equation that's easy to generalize to higher degrees. So a polynomial of degree n can be represented using a symmetric nth-order tensor and the mode n product. We can also represent a non-homogeneous polynomial using a tensor through homogenization. We assume that the tensor containing the polynomial coefficients can be well approximated by a low-rank palyadic decomposition. Real data is often low-rank due to inherent structure. For example, user ratings of movies are low-rank because users behave in similar patterns. Therefore, we can obtain accurate results with a low-rank coefficient tensor while greatly reducing the amount of model parameters. We obtain the equation of the model by substituting a polyadic decomposition for the tensor in the reformulated equation of a multivariate polynomial. We use a symmetric polyadic decomposition, which has even fewer parameters than a normal polyadic decomposition, since this tensor is symmetric. By increasing the amount of rank 1 tensors, the model is able to better approximate more complex data, at the cost of having more model parameters. Therefore, the amount of rank 1 tensors determines a trade-off between accuracy and the computational cost. In this figure, we see that the amount of parameters of the model is not exponentially dependent on the degree and the amount of variables, unlike a multivariate polynomial. The equation shows that the amount of parameters is linearly dependent on the amount of variables and the amount of rank 1 tensors after the substitution of a symmetric polyadic decomposition. To be able to fit our model using a nonlinear least squares approach, we first have to reformulate the problem as a linear system. Naturally, the model should approximate the data for each entry in the training set. By stacking all these equations, we obtain a linear system with a quadrilateral structured coefficient matrix and a symmetric polyadic decomposition structured solution. We use a Gauss-Newton algorithm to minimize the square of the residual, where the residual is the difference between the left-hand side and the right-hand side of this structured linear system. We use a Gauss-Newton algorithm because it converges quadratically near the solution and it's more robust to initialization. This algorithm requires the computation of the cost function, the gradient, the Jacobian, and the Gramian as an approximation of the Hessian. We exploit all structure of this linear system to efficiently compute all ingredients for this algorithm. This results in greatly reducing the computational complexity of the algorithm, since the cost of the most expensive step goes from exponential dependency on the degree n, when we are not exploiting all this structure, to the amount of variables I to the power of 3 for the model where we do exploit all structure. We have also developed an algebraic algorithm to compute the parameters of our model. We can use the solution obtained with this algebraic algorithm and refine it by using it as the initialization of the optimization-based Gauss-Newton algorithm. The algebraic algorithm consists of two steps. First, we compute the unstructured polynomial coefficients, and then in the second step, we reshape them into a tensor, and then approximate this tensor with a low-rank symmetric polyadic decomposition. To test our model, we use it to approximate the Gibbs free energy of a metal alloy. We see that both the models computed with the optimization-based and algebraic algorithm accurately approximate this data, while only requiring very few samples of the training data. So to summarize the presentation, we have developed efficient algorithms for multivariate polynomial regression by approximating the coefficients of this polynomial with a low-rank symmetric polyadic decomposition. This decomposition is crucial to the efficiency of the algorithms since it allows us to break the curse of dimensionality. This summary is really the take-home message of the entire presentation. This was it for my presentation. Thank you very much for listening.